Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Hello, good day. Welcome to Pastor Victor Academy. I'm glad you're watching. In my previous video, I talked about properties of pure substances and we looked at some of the characteristics of TV diagram and PV diagram. In this video, we'll be looking at the vaporization processes of pure substances. So please do want to pay attention as we go on. You'll be learning a lot in this video. So the first one we want to look at is the TV process, that's temperature specific volume process. Generally, at constant pressure, the volume of a pure substance increases with increasing temperature, though the relationship is not usually linear or proportional. So what that means is that once pressure is constant, as the temperature of a pure substance is increasing, the volume usually increases. But the issue is that the increase in volume may not always be proportional to the increase in temperature. But just expect that increase in temperature would always cause the volume of a pure substance to increase at constant pressure. So we'll be using water as a case study. And in this process, we'll have a piston cylinder assembly. This is a cylinder and this is the piston. Or this is the water inside the piston cylinder assembly. So all of this is our system. Then under the piston cylinder assembly, we have a flame, that's the fire that supplies the heat. Now, I want you to note that the mass of water in this system is constant. Throughout the process of heating, it will not change. The mass will always remain the same. Why? This is a closed system. It does not allow matter to flow out or flow in. So that's why we have this. So as we are supplying heat to the system, we observe what happens. Now, look at the graph we have. This for 1 atm and this for 2 atm. So when we are working with a pressure of 1 atm, this is the graph we would have. But when I'm working with a pressure of 2 atm, this is the graph we would have. So we'll have our initial temperature as 50 degrees here. Then we'll have a temperature of 100 degrees here and a temperature of 120 degrees here. So what happens as we begin to heat? Now, you notice that our initial volume is either Vx or Vy, depending on the pressure we are working with. If you are working with a pressure of 1 atm, then the initial volume will be greater compared to when you are working with a pressure of 2 atm. The reason being that when temperature is fixed, then what determines the volume is pressure. So when there is higher pressure, volume reduces. And when there is lower pressure, volume does what? Increases. So in the case of 1 atm, the pressure is lower, which means that the volume will be what? Greater. Then here the pressure is what? Greater, which means that the volume will be what? Lower. So our initial volume will depend on the pressure we are working with. Now, we want to start with a pressure of 1 atm. And remember that the pressure is fixed for this process. So we said we are working with a constant pressure of 1 atm. So in that case, we begin. Our initial volume becomes Vy at a temperature of 50 degrees C. We begin to supply heat. As we are supplying heat, the temperature of the system begins to rise. And as the temperature is rising, the volume is also what? Increasing. Now, because the mass is constant, specific volume is also what? Increasing. So the temperature continues to increase until we get to the point of saturation. And that point of saturation is 100 degree Celsius. Why is it 100 degrees Celsius? because we are working with a pressure of 1 atm. So once the pressure of water is fixed at 1 atm, as you begin to heat it, it will reach the point of saturation at a temperature of 100 degrees Celsius, as long as that water is pure. So when it gets to this point, you can see that the volume increased, the volume changed. So what we have here as the volume is no longer V1. The volume has what? Increased. So at this point, what is actually happening? Water is boiling. So what boiling means is that the liquid is changing to gas or to vapor. So liquid water is changing to what? Vapor. And that begins at this point. That's the saturated liquid curve. So as the heating continues, you will notice that the temperature of the system will no longer rise. Not because heat is no longer supplied, but because the system is utilizing the heat to break intermolecular bonds. So instead of causing a temperature rise, it is causing a change in what? Volume. Why is there a change in volume? As the bonds are breaking, we are having more vapor. And vapor would occupy a larger volume compared to what? Liquid. So that's what happens. As we are supplying heat, at this point, temperature remains constant and pressure already is what? Constant. So here we are having constant temperature and constant pressure what? Process. So the temperature is fixed at 100 degrees. It continues like that until the whole water in the system changes to vapor. And when that has happened, that means we are at this point of the saturated vapor curve and we have a new volume, Vk. So that becomes the volume of the water in the system because vapor would occupy a larger volume compared to liquid. So at this point, the whole water in the system has changed to vapor. Now we observe that as heat is supplied, the temperature begins to rise again. So here the temperature was rising until we got to the point of saturation. Then the temperature stopped rising and we had a constant temperature and pressure process until this point. Then the temperature begins to what? Rise again. And as that is happening, the volume of the vapor is what? Increasing. Because the volume of a gas is very sensitive to change in temperature. So that's what happens at the pressure of 1 atm. Now let's see what happens as we work with a pressure of 2 atm. So the first thing is that we want to start with the same temperature, that's 50 degrees C. And when we start with the same temperature, what happens is that the initial volume would be lower. I've already told you the reason, because we are working with a higher pressure. So when pressure is high, volume is low. And when pressure is low, the volume is high. That's when we are working with the same temperature. So since we are starting with the same 50 degrees C, with a higher pressure, our volume would be lower. So Vy is greater than Vx. And in this case, our initial volume becomes Vx. So what happens? We begin to supply heat to the system. And as we are doing that, the temperature is rising. And as the temperature is rising, the volume is also what? Rising. So at this point, water begins to boil. Now, unlike when it was at 1 atm and water was boiling at 100 degrees C, if you've watched my previous video, I said as pressure is increasing, boiling point will also what? Increase. You don't expect the same boiling point for different pressure. So once you fix your pressure, that is what determines the boiling point. So when we had 1 atm, our boiling point was 100 degrees Celsius. But when we had 2 atm, our boiling point increased to 120 degrees Celsius. So at 120 degrees Celsius, water begins to boil. So it has reached saturation. Now, when you compare these two graphs, you notice that the volume at saturation for 120 degrees Celsius is greater than the volume at saturation for 100 degrees Celsius. The reason being that when the pressure is low, water reaches saturation on time. So the change in volume is not really much before what? Saturation. But as pressure is increased, water will not reach saturation on time, which would result to a reasonable amount of change in volume compared to the one of lower pressure. So here, the same thing happens. Temperature remains constant. So even though heat is being supplied to the system, the temperature will no longer what? Increase. And that's still because the system is using the heat supply to break intermolecular bonds of water. And as that is happening, the volume of the system is what? Increasing. So here we are having constant temperature and pressure. And volume is changing because what liquid water is changing to gas, and gas would occupy a larger volume. So that keeps happening until we get to this point. That's the saturated vapor curve. So at this point, the whole liquid in the system has changed to vapor. And at that point, we are having a new volume, Vj. Now, that's another thing you have to note. In the case of 1 atm, we had Vk as our volume, but in the case of 2 atm, we had Vj as our volume. So you can see that the volume for 1 atm at the saturated vapor curve is greater than the volume for 2 atm at the saturated vapor curve. The reason is because of the pressure difference. So 1 atm will give room for more expansion in the volume of vapor, which makes the volume greater at the saturated vapor curve. So after the saturated vapor curve, the volume of vapor continues to increase as the temperature of the system is increasing. Now I want you to take note of some things. Look at this. The slope of the lines here are not the same as the slope of the lines here. This is the compressed liquid region, whereas this is the superheated vapor region. Now, in this case, we are having greater slope compared to this part of the graph. And the reason being that the increase in the volume of liquid with increase in temperature at fixed pressure is always small. So liquid has strong intermolecular attraction. So that's why we discovered that we have a greater slope here, indicating that we need a high temperature difference to produce a small change in volume. Now, here, volume changes reasonably with increase in temperature. Another thing you also notice is that the slope of this line is not the same as the slope of this line. The slope of this line is greater compared to the slope of this line. And that's because in the case of 1 atm, we'll have greater change in volume with increase in temperature. So that's why we're having Vk greater than Vg. And the thing continues here because the pressure gives room for greater expansion in vapor in the sense that it is lower. But where we are having higher pressure, the change in the volume of vapor is reduced. So that's why the slope is greater here, whereas the slope is lower here. So the lower slope is indicating that there's a greater change in the volume of water as temperature is increasing. So that's it. Then I also want to explain why we need to use specific volume instead of normal volume for our graph. And you also notice that on the property table, that's what you find. You don't find volume, rather you find specific volume. So why we work with specific volume instead of volume is because if we are working with volume, that means we need to know the value for different amount of water. So you can imagine when you are working with a glass of water, 2 glasses of water, 3 glasses of water, because the change in volume is always proportional to the quantity of water. So you now want to know the volume increase for 1 glass, volume increase for 2 glass, volume increase for 3 glass, and that will not make sense. You get so, but when you're working with specific volume, is constant, irrespective of the amount of water you're working with. So if we are working with 2 liters of water and a pressure of 1 atm, we'll have the same graph. If we are working with 10 liters of water at 1 atm, we will have the same graph. So if you check the value of V on your property table for a particular pressure and temperature, it applies to whatever amount of water you are working with. So what you just need to do to get your volume is to multiply V by M. That gives you your what? Volume. That's to multiply specific volume by the mass of water you're working with. And that gives you the volume of the liquid. Now, here we also have what we call the critical temperature and the critical pressure. So we're having 374 degrees C and we're having 220.6 watt ATM. So once you fix your pressure at 220.6 ATM and you begin to heat the system, the temperature keeps rising until you get to 374 degrees Celsius. At that point, water is said to be in a critical state. It's called a critical state because vapor cannot be differentiated from liquid again. So once the temperature rises above that 374 degrees Celsius, water becomes a supercritical fluid. What that means is that it is no longer in the liquid phase nor in the vapor phase. Now I want you to look at this. Here we have partial derivative of V with respect to temperature at constant pressure. So this is for TV graph. So what this is telling us is the ratio at which vapor expands compared to what compressed liquid. So you can see the ratio is 20:1. So what this means is that the change in the volume of vapor for change in temperature at a particular pressure will be about 20 times greater than that of compressed what? Liquid. So that shows you how sensitive vapor is to change in temperature compared to what? To liquid. So that is the TV process. Thank you for watching. I really appreciate. Please do well to like, share, and subscribe. Help me share. I want to reach more students. And don't forget to subscribe. Once again, thank you for watching. God bless you.